I'm pleased to have Edson Wendland on the podcast today. And Edson is a professor in the School of Engineering in San Carlos University within the Sao Paulo system, and previously served as director of the engineering school from 2019 through 2023, and survived COVID. So I think that was an interesting time. The school celebrated 70 years last year, which is great. And Edson also served as the state coordinator for science, technology, and innovation in 2023. And we recently met at the Groundwater conference in Sao Paulo, and I really enjoyed the visiting. Edson's research covers groundwater surface water interactions in the Guarani aquifer, impacts of land use change and climate change on water resources in Brazil. Today we're going to cover many different topics, and we'll start with the current drought in Brazil and talk about previous droughts and how they manage the water resources in response to those. And then Edson will give us some background information on Brazil and talk about the aquifers and the surface water systems, and then linkages with energy through the hydroelectricity and also to food production through irrigation. So thanks a lot, Edson, for joining me today.
Well, thank you so much, Bridget, for this invitation. It's really a nice opportunity. I'm really proud of taking part in this podcast and talk to you again after your visit in Brazil. Was really nice, really successful. We enjoyed a lot your visit, and even the students had they took this opportunity to talk to you personally, and it was really nice, really great. And now this follow-up in this podcast is really a nice opportunity. So thank you very much for this podcast, for this talk.
Yeah, it was really fun to go out in the field and to see all the different the eucalyptus plantations, the sugarcane, and all of those, and to see all the research that you guys are doing. So Edson, you're currently in a really severe drought in Brazil, and it's pretty scary. So maybe you can describe what's going on, and maybe some of the potential causes of this drought or the impacts also.
Okay. Well, first of all, I will give you some numbers of Brazil. Perhaps people is not very confident with the Brazilian size and all that. So Brazil nowadays is a population of around 210 million people living in an area of 8.5 million square kilometers. It's a little bit larger than the connected states of United States of America in terms of size as comparison. So it's formed by 26 states and the federal district, and the official language is Portuguese. The capital is Brasilia, as most of you know, and the largest city is São Paulo. And São Paulo, there are 12 million people living in this city, and all the neighborhood altogether is around 18 million people living in a close, very compact neighborhood. And of course, they have some problems, difficulties with water supply. Brazil was a Portuguese colony that had been discovered in 1500 by the Portuguese Pedro Álvares Cabral, and got to independence from Portugal just in 1822. And then we started a local monarchy with the Emperor Pedro I, and after that his son, Pedro II, had lived until 1889. And since then, we are a federal republic. Well, the climate conditions, normally we have a temperate temperature climate in South Brazil, and evolves through the different tropical, subtropical, tropical conditions, and also equatorial conditions on the equator line that crosses Brazil exactly on the north. And due to that, we have different biomas, ecosystems in Brazil, starting from grassland, mainly in the south, and then forest even in the south and in the coast. In the central region, we have more what we call cerrado. It's a mixture of shrubland with some trees, larger trees, smaller trees, and this system covers around 22% of the Brazilian area. And then we also have the Amazon region, and this is the largest one. It's around 4 million square kilometers, and almost everybody knows about the Amazon region. It's plenty of water, moisture, and large trees. Well, of course, it's a very diverse system with different climatic conditions and different biomes. And sometimes we have some difficulties with the droughts. And that's exactly the problem we are facing just now. The drought in this year is very severe. Actually, it started already in 2023, 1 year ago, because the rainy season at the end of the year, to 2023 to 24, was not really intense, a little bit dry. And now we are in the following period due to this lacking of atmospheric water, mainly. And the reason for that is that we have a stronger combination of warmer temperatures in the oceans. At one side, the El Niño effect in the Pacific Ocean that impacts the climate conditions in Brazil. And we are more or less used to that, and the changes are not that strong. But specifically in this year, we have another system acting, and that's as abnormal higher temperatures in North Atlantic. So the combination of the warmer waters in North Atlantic with the warmer waters in the Pacific combined are changing our climate system very strongly. And as a consequence, in the Amazon region, we have probably the strongest drought period and more intense since it has been monitored. We have some data from the 70s or even from the 50s of river levels monitored in Manaus, Porto Velho, that are main cities in the Amazon region. And these streams are reaching the lowest level already observed. It's below the minimum record already observed. So the Amazon region is very dry. And as a consequence, the Southeast Brazil, Central Brazil, and Southeast Brazil results also drier because we have a system of atmospheric rivers, which we call the flying rivers, that transport moisture from the Amazon region down to the south, to the southeast, even to Argentina, Uruguay, South Brazil, Southeast Brazil. All these areas are supplied by water from these atmospheric streams from the Amazon. And in this year particularly, the Amazon region is dry. There is, due to that, there are many fire spots producing large amounts of smoke. And instead of transporting water to the south, these atmospheric streams are transporting smoke. So we also get smoke from the North Brazil, from the Amazon region, and that's affecting all the water quality in the south and especially Southeast Brazil, here where we are in São Paulo. So everywhere is quite dry. At the moment I am looking there, our relative humidity is around 15% at the temperature of 36 degrees. It's very warm, hot, and dry. And the possibility to occur more fire spots is larger. Everywhere is getting spot fires. As a consequence of all that, around 5 million square kilometers is an area larger than half of the United States, has been affected so far by dry, fire, and smoke. And as a consequence, the air quality is really bad everywhere.
Yeah, it's a pretty crazy situation, and thanks for providing the background in Brazil. Sometimes it's difficult to understand different regions, but it's nice to put it in the context of the U.S. Similar area, population slightly or smaller than the U.S. And Portuguese, the language. So it means I'm pretty lost when I'm down there. But it's nice to understand the relationship between the climate and the biomes then. And of course, everybody hears about the Amazon, but the Cerrado is a very important region, is maybe not as protected as the Amazon. And so there's a lot of agricultural expansion in the Cerrado. And so that's a really important issue also. And the recent drought, you mentioned that rivers at their lowest levels in the Amazon region. And I think I prefer the term flying rivers than atmospheric rivers. It seems more fun. Thousands of spot fires, I guess, and then reading about fish kills in different rivers and things like that. So, and the linkage then is that the warm Pacific linked to El Nino, and also the warm North Atlantic changing the atmospheric circulation. Edson, your student, previous student, Davi Mello, visited us in Austin many years ago when you had a drought in South Brazil, in Sao Paulo region, and that was a really critical situation for Sao Paulo. Maybe you can describe that a little bit.
Yeah, okay. That's really nice. It's a really interesting question, and that's the reason why we asked you for support, because we started to use GRACE data to evaluate the loss of moisture, of water during that period. And it was also an El Nino system. And as I mentioned, we have this atmospheric river, a flying river from Amazon to the southeast, and that provides moisture to Brazil. And during this period, 2014-15, we had a blockade of this atmospheric system due to high pressure over central Brazil. And this atmospheric moisture, flying river could not reach to São Paulo state. So we had less precipitation during our humid period that runs from October to March next year, more or less. In general, we have a precipitation around 1,500 millimeters. And during the summer, we had a lack of around 300, 350 millimeters, just to have 1,200 millimeters rainfall. And that was not enough to replenish all the moisture in the soil, and even to fulfill the reservoirs for water supply. So then the reservoirs that are used to provide water to São Paulo, it's a water basin transfer of around 30 cubic meters per second is transferred from one water basin to the city of São Paulo. Suddenly, we could not rely anymore on the supply because the reservoirs had not enough water. So it was really difficult. A population of 15 million people, 18 million people living there. Of course, there are another sources, but this was the main one. And suddenly, it was not there anymore to supply water to the people. And this difficulty run from 2014 through 2015 until 16 when it started to rain again. So we were not prepared to this situation. And well, now we provided some additional sources. The São Lourenço system to the south of São Paulo is connected, although a basin transfer system is working nowadays. And also the Paraíba do Sul River is a stream that starts in São Paulo and flows to Rio de Janeiro, and is also important to supply water to Rio de Janeiro. It's the same water basin, and there are some 8 or 10 million people living there that also rely on these water sources. Anyway, all these different sources have been connected, and now the system in São Paulo is more resilient. But if you lack the recharge in some area, the other one may supply during a certain period. But it was, of course, really difficult. And the reason in 2014-15 was a blockade in the atmospheric system. And again, the flying river from the Amazon didn't reach our region in southeast.
Right. And so, I mean, it's interesting, Sao Paulo almost completely dependent on surface water reservoirs. The Cantarera system of reservoirs, maybe 5 or 6 reservoirs, or maybe even more. I don't. But similar to Cape Town, also almost totally dependent on surface water reservoirs. And then I think some of those reservoirs were down to maybe less than 10% of capacity during that time. But what you described, I mean, you said normally 1,500 millimeters of rainfall, which is about almost 60 inches in our system here. And then maybe just a 300 millimeter reduction during that time, but still had such a huge impact. And people here would think maybe 60 inches of rain is quite a lot, but then your relative humidity is in the dirt. You only have 20%, 15% relative humidity. So it's difficult to understand, but it's nice to see that you have been able to connect then to these other river basins, and so that would make you more resilient to droughts. So that's good. I mean, some people may look at Sao Paulo and see it's next to the coast, so how come you're not desalinating seawater? And I think, maybe you can describe that a little bit.
Yes, okay. Well, concerning the water balance, although we have a large rainfall and would say 1,300 millimeters or 1,200 millimeters is a lot of rain, with a lot of water. However, we have too much energy, sun energy and wind energy, so the evapotranspiration potential is high. The air is dry, the relative humidity, so the evapotranspiration potential is really high, and depending on the culture, it reaches 1,100 to 1,200 millimeters on evapotranspiration. So the plants are taking out all the water to survive, and it doesn't remain so much water for runoff and infiltration. That's one reason that in 300 millimeters or 400 millimeters less rainfall has this great impact. There are in São Paulo also many wells, private wells that are not operated by the public supply, and many companies operate their own wells. And the difficulty there is that there's not a really effective management of the use of groundwater to control that, because the wells are drilled inside the properties, private properties, and many times you don't see the wells from outside. But there is an estimate of around 2,000 wells, private wells drilled in São Paulo. And they also provide water. There is a São Paulo basin, a sedimentary basin there. It's not that huge, but it provides groundwater. And there is an estimate of around 10 cubic meters per second of pumped water through these wells. It also helped to survive the period of drought in 2015. Now, concerning the idea of desalination, for São Paulo, it is difficult. It's close to the coast, around less than 100 kilometers. However, there is a very big difference, head difference. São Paulo is almost 1,000 meters above the sea level. So if you do the desalination at the coast, the water has to be pumped up to São Paulo. And then we would need a lot of energy to pump this water up to the city. So that's the reason why desalination is not being considered that much in São Paulo.
But you also mentioned, Edson, that, the Guarani aquifer is another potential source for Sao Paulo, and maybe you could transport water from the Guarani to Sao Paulo. What?
Yes, is also a possibility. I would say the Guarani aquifer, the border of the outcrop zones of the Guarani aquifer system, is around 200 kilometers away from São Paulo. And of course, on the outcrop zone, perhaps you can produce more water with a battery of wells and transport this water to São Paulo through a pipeline. But perhaps it would be easier to divert water from the watersheds close to São Paulo, and then with the Guarani water supply the cities that are located in the other watersheds that supplied water to São Paulo, to do a transfer from one watershed to the other. That would be a possibility. And in this case, it would be possible to transport Guarani aquifer just by gravity without the necessity of large amounts of energy, just to elevate the water from the aquifer, from the sandstone, and put in the pipeline and transport by gravity down to the other city. It would be a possibility. And so transport water from one watershed to the other. That could be a nice possibility, yes.
So another aspect of water is the linkage with energy production, and a lot of people tout Brazil for having so much renewable energy, and from hydroelectricity, maybe almost 2/3 of their electricity generation from hydroelectricity. But you're seeing now in this current drought that some of the hydroelectric power plants are in trouble, and so maybe you can describe that situation a little bit. The vulnerability of the electricity generation to the droughts and that sort of.
Yes, perhaps I can tell a little bit about. Brazilian is supplied mainly by hydroelectric power plants. I'm starting the other computer here. And the hydroelectricity represents 66% of the Brazilian energy production. And the other sources like fossil energy and solar energy and wind energy represents 1/3 of the production. 2/3 is hydroelectric energy. Up to the 70s, the dams were constructed to store water, surface water, during the wet periods and produce energy with a higher waterhead difference. So producing more energy with more effectivity. The most known electric power plant is Itaipu. It's in the Paraná Basin between Brazil and Paraguay. And this was the main energy supply for a long time. And Itaipu provides 12 gigawatts hour on energy is really important for Brazil. It's around 10% of the total energy production in Brazil. We consume around 110, 120 gigawatts hours in Brazil. Well, and this Itaipu building has an enormous reservoir and can manage this varying input of water into the system, the reservoir. We have many different dams of this kind. Since this millennium, I would say, we started to build also dams for energy production, hydroelectric energy production, more to the North Brazil, close to the Amazon region. And due to the environmental concern of flooding enormous areas of forest, the Brazilian government decided to build hydropower plants operating only with the runoff of the river, only the normal discharge without any reservation. So the consequence for that is now that we are facing such a severe drought in North Brazil, many of these power plants reduce it strongly, more than 90% the energy production. I will give you an example. There is the Madeira River, is an affluent of the Amazon River, and it drains all the area of Bolivia, Peru, and then flows into Brazil. In the city of Porto Velho, is already in the Amazon region. There is a dam there for energy production. It's called Santo Antônio. And normally, this power plant produces 4 gigawatt hour with the discharge, the normal discharge. Due to the present drought in this watershed, the water level reduces to the lowest level ever seen. It has never been measured. It's just 40 to 50 centimeters. It's not being monitored every day. And the lowest level has been 1 meter or so, not a long time ago. But during a period of 70 years of monitoring, now we are seeing the lowest level. So also the lowest discharge. The consequence of that is this power plant, instead of producing 4 gigawatts, is producing 150 or 200 megawatt. That means it's a reduction of 90% of hydroelectric power plant power production. And we have to supply this energy demand by thermoelectric power plants that are run by fossil fuel, like oil or gasoline, not normally oil. So that's a strong environmental impact nowadays because we don't store enough water for this dry period. And we have to run some unsustainable systems of energy generation. And we have many examples of hydroelectric power plants operating like this.
Right. And I guess, the difference between water systems and electricity systems is that the electric grid is highly connected. So I guess if you have shortages in one area, then you can connect with you're connected with other regions. So that can help even out the supply to meet the demand.
Yes. All the Brazilian energy supply system is interconnected from the south to the north. There are 26 states connected. Just one state is Roraima. It's close to Venezuela. It's not connected so far to the system. So they need thermoelectric energy generation and all that. But all the other countries, states, are connected to the same system. And this Santo Antônio power plant that reduces enormously the energy production, transports energy to Southeast Brazil. And that's a high voltage transport line of around 3,000 kilometers to transport the energy from Amazonas to our region in central Brazil, southeast.
Yeah.
Yeah,
That's
of course.
yeah.
They are all interconnected, and sometimes when we have a big problem in one part of the system, it also impacts other regions that are really far away.
Right, right. Well, I mean, Brazil is has probably one of the lowest carbon footprints for their electricity generation of any country, and so that's really nice. And you're mentioning that switching from traditional large reservoirs and hydroelectric generation that way to run of the river hydroelectricity makes you more drought vulnerable than without that storage. But there's trade-offs in everything. So environmental impacts are reduced, but then the energy security may not be so high. But I mean, when I was looking up the numbers, it seemed like in last year in 23, only 5.5% was generated by natural gas, and you had maybe 8% biofuels. You have a lot of sugarcane. I don't know if that's the source of the biofuel electricity. And then wind was about 13% and solar about 7%. So really nice renewable portfolio in Brazil relative to most other countries. So thanks for providing all the background and all of those aspects, but now getting down to what you really do, and working with groundwater. Maybe you can describe the groundwater system in Brazil. You have a lot of aquifers, but most people only know about the Guarani system. And so maybe you can describe some of those aquifers.
Yes, okay. Well, the Guarani aquifer system is more known, I think, due to the international impact during an international project with the Global Environmental Fund, and so a lot of discussion about the Guarani aquifer system, which is a sandstone system that has been covered by basalt outflow during the Cretaceous. So the Guarani aquifer is 10% unconfined and 90% of the system is confined by basalt. It used to be an aeolic sandstone, so with high porosity and high hydraulic conductivity, and a huge extension, extending from Argentina through Uruguay, Paraguay, and Brazil in 8 states in Brazil, with a total area of 1.2 million square kilometers. As a reference, is perhaps 1/6 of the United States area. As a comparison, it's really large. And the thickness of this aquifer varies between 50 meters in the outcrop zones up to 800 meters in the central basin. It varies linearly. And with a maximum depth of supposed 1.8 kilometers, and that's in Argentina. And in this area, we don't have that much information. That's the reason why we suppose it's 1.2 million square kilometers, is the geological formation. Of course, over such a big area, there are some compartments and arcs and all this geologic deformation. And we are still studying the interconnection of the whole area, just to see if the water from Brazil is really flowing to Argentina or not. And the point is then we have to identify the recharge areas and, more importantly, the discharge areas. And that's some problems, some questions that we are studying still now and doing some isotopic measurements and looking at the age of the water. And at certain points, we come up to 500,000 years of the water, the really fossil water. On the other hand, at the outcrop zones, the water is relatively young and is being normally recharged all the time and pumped some kilometers away. There is an estimate of the total amount of water, and it's supposed to be something between 25 and 35,000 cubic kilometers. It's a very big amount of water. And, well, the water is there, and there are some discussions about the available technology to pump up this water. There are some limitations. The total volume may be that, but we have still we have to study the recharge of the system and how sustainable it really is.
Right. Yeah. I mean, those old ages up to 550,000 years from Krypton dating. I mean, if you're pumping that water, you can forget about the recharge.
Exactly. And even here we are in São Carlos, we are close to the outcrop zone. We do some monitoring of groundwater level variation, some piezometers in the outcrop zone. And even here close to our city, some isotopes indicated an age of around 10,000 years for the water from the Guarani aquifer system. Well, this is really complex. We probably are below a seal of diabase, and now we drill through this diabase, and we are pumping the water below this diabase, and it's older than expected.
And they're about, I mean, maybe the Guarani got a lot of attention because it's a transboundary aquifer, and you mentioned the Jeff funding and all of the interest in. So it certainly is probably the most known. But you've also got other aquifer systems. You've got about 27 different aquifer systems. We visited the Baru when I was there this time, and you also further north maybe the Uruguay and then the one in the Amazon. Maybe you can describe those a little bit, Edson.
Yeah, okay. Well, just to mention the extension of the Guarani aquifer system, 1.2 million square kilometers, is more or less 3 times as larger as the High Plains aquifers in the USA. So just to give a reference. Well, this is why it got so much impact, this aquifer. Well, here in São Paulo state, the Guarani aquifer system, as I mentioned, is covered by this basalt layer, and this basalt layer may grow up, going to the west from east to west. It grows up to 800 meters of a basalt layer covering the Guarani aquifer system. So you have to drill really deep to get water from them. And then you get warm water at a temperature of 45 degrees centigrade, more or less. And to distribute this at the temperature nowadays, we are at 36 degrees. It's not really nice to do water, but okay. So the basalt is covered by another sandstone system that we call the Bauru system. It has a smaller extension and covers mainly here in the São Paulo state and northern of Paraná state, with an area of around, I would say, 300,000 square kilometers or so. And the thickness is around 200 meters of also sandstone. It's from the post-Cretaceous, from this period. But it's really important because the recharge occurs naturally on this Bauru system. And it is shallower. And many cities in the state of São Paulo, and that's the reason why most of the cities in São Paulo state use groundwater, because the Bauru aquifer system provides water and an acceptable depth. Around 150 meters is enough to pump water from the Bauru system. And for example, there is a city to the west of São Paulo state. It's called São José do Rio Preto. There are more or less 500,000 people living there. And they must have around 2,500 private wells owned by the different buildings um, and condominium, and they provide their own water from this Bauru aquifer system. It has a higher replenishment because it's a not unconfined aquifer, and you have recharge over the agricultural areas and can provide water for the cities. Many of the cities to the east, to the west in São Paulo state are provided by groundwater. Another example is Ribeirão Preto. It's a city with around 700,000 people living there, and they rely exclusively on the Guarani aquifer system because they are really close to the outcrop zone, and they have been using the Guarani aquifer system for 100 years, since 1920. And they are still relying on this groundwater system. So Bauru and Guarani are really important for the state of São Paulo. But of course, there are another aquifer systems that are really important. And one, as you mentioned is the Urucuia aquifer system. The location is more in the estado da Bahia, is more to northeast Brazil, closer to the coast, but also close to the central Brazil. And that's the area of Cerrado, where we used to have Cerrado. And since we had some improvement on the production of seeds for soya production and corn production and cotton production, they are better adapted to climate conditions of the Cerrado area. Since then, they started to occupy the Cerrado area for agricultural production. It's a really flat land, good for mechanization, a lot of energy because we are above the tropical region, between the tropic and equator. So there is energy, there is land, it's flat, good to mechanizate, and what they need is water. And the water they found in this Urucuia aquifer system, which is a big sandstone with an area of 76,000 square kilometers, really large, a thickness between 250, 350 meters, so in average 300 meters, an area of 76,000 square kilometers, an estimate of 4,000 cubic meters of water. And so they have water there to develop the agriculture. And this area uses a lot of irrigation for agricultural production. It's increased in the last 20, 30 years. It's the frontier of development of the agricultural production in Brazil. It's amazing how much they developed and started producing food. Nowadays, Brazilian is a big exporter of water due to the expansion of agricultural activity over the Cerrado area. And then the problem is really the water supply. They are taking water from the Urucuia aquifer system, perhaps too much, but there is still some recharge there. The rainfall in this area is around between 800 and 1,200 millimeters a year. So there's enough rainfall, there is recharge, and we have to understand a little bit more what is the water balance there, the sustainable, in order to maintain the system resilient. But the idea is to increase the use of water for irrigation and improve the food production, perhaps to supply food for the world. I don't know.
Yeah.
And then I will mention also the great Amazon aquifer system. It's a new idea, more or less. The Amazon basin is big. It's around 4 million square kilometers, or even more than that. Half the area of the United States is Amazon basin. And this is also sedimentary basin. The Andes have been eroded and transported by the Solimões River, and then it turns up to Amazon River and is transported to the coast, all the sediment. So it's an unbelievable large sediment base. And now they have been studying these isolated systems, the Solimões Formation, the Amazon Formation, Alter do Chão Formation. These are all geological formations, all sandstone mixed with some siltstones or some silty layers, and of course, as heterogeneous as the geology normally is. But all of them are sedimentary sandstones that contain water. And they decided to call all the system the Great Amazon Aquifer System. The acronym for this in Portuguese is SAGA, Sistema Aquífero Grande Amazônia. And they are proud that it's larger than the Guarani Aquifer System, and perhaps contains more water than the Nubian sandstone. Because it's really large. It's 1.3 million square kilometers, a thickness of around 600 meters. They suppose porosity of 20%, an estimate, and they should have 160,000 cubic meters of water stored in the system. This is also the water that supplies water for the vegetation in this Amazon region, to large trees and plants that use this water, evapotranspirate, put the moisture in the atmosphere, and then this atmosphere flies to South Brazil, to Southeast, and provide the rainfall that we need here. So apparently everything is really connected. So, and this Great Amazon Aquifer System is an idea of around 10, 20 years just. And there is still a lot of research that has to be done to understand better the system, to maintain it resilient and sustainable.
Wow, that's incredible. I mean, the groundwater resources are amazing, and you've also got a lot of surface water resources, so you're really endowed with a lot of water, and then trying to manage it sustainably will be challenging. One of the things that I would like to get back to is, your work on the linkage between land use and groundwater recharge. I mean, we all know it's very important how fast these aquifers replenish, and so you have done quite a bit of work on the outcrop area of the Guarani and looking at the different types of land use. And I was really impressed looking at, these eucalyptus plantations and the coffee plantations, sugarcane, all of these, such a variety, and all of these different types of land use then impact the recharge and the partitioning of water at the land surface when you change from cerrado in this region to these crop vegetation. Maybe you can describe that a little bit, Edson.
Yeah, okay, thank you. Well, as you mentioned, we started a research project in one of the Guarani aquifer outcrop zones. And we are lucky that we are not far from this area, it's around 15 to 20 kilometers away. And we started during this big discussion and rediscovery of the Guarani aquifer system at the beginning of the millennium, 2002, 2003, more or less. We started to discuss this aquifer system. And they had there in this Global Environmental Fund a program for the universities. So small seed money for the universities to do some research too and take part in the program. And we were lucky that we got some supply. I think it was something like $20,000 or so. And with this money, we started a monitoring system in our watershed that we call Ribeirão da Onça. It's the stream of the panther, more or less like this. And we started to drill some wells in different land uses. And at that time, we had there eucalyptus, sugarcane, citrus, orange mainly, and pasture, grassland for cow production, and also natural vegetation, cerrado. And we drilled wells in all these different uses and monitored during a long period what is the groundwater level variation. And then we applied this single WTF, water table fluctuation method, to estimate what is the recharge under different land uses. And it has, at the beginning, has surprised us that we measured, although the precipitation is the same, quite homogeneous, we had different variations on the groundwater level. And since then, we started to understand better what is the impact of the land use on the groundwater recharge. And actually, what is the impact of the land use on the distribution of the water in the different compartments. So if we have a smaller vegetation like grassland, the evapotranspiration is smaller, and is a system that allows infiltration, we will have more recharge. And when the vegetation increases, like sugarcane or orange trees, there is a little bit more evapotranspiration, but there's some runoff, and there is also infiltration. And then if the vegetation grows more up to the size of eucalyptus, or even a natural forest, like cerrado, dense cerrado with trees, the evapotranspiration is high, up to 1,000 millimeters a year. There is interception, evaporation, and moisture in the soil, and also evaporates. But at the end, from the total precipitation of 1,500 millimeters, we have perhaps just 100 millimeters as recharge. On the other hand, with grassland, we have observed 400 millimeters a year in recharge. So then we started to understand this better. How do land use impact the distribution of water in the different compartments? The large trees are important to take water from the soil and bring it to atmosphere to control the relative humidity. On the other hand, when we have grassland, we store the water in the ground and may use it later as a reservoir of water. So we started to try to understand this. From this project, we went up to the problem of runoff and erosion and built different experimental plots with 20 meters long, 5 meters wide, triplicates with all these different cultures, the traditional cultures there: sugarcane, pasture, soja, and fallow land. And compared, was it the impact of erosion and runoff under these different uses of soil? So then we tried to build a table of the trade-off between the different uses in terms of erosion and in terms of water balance. What is consuming more water, where the water is going, the partitioning of water under different land uses, and what is also the impact on erosion. At the end, after, since we started in 2004, this monitoring, we could monitor it continuously, getting funding and support from another agencies, the Brazilian agencies and state agencies here. And since then, we have been monitoring continuously. We have nowadays a series of 20 years of precipitation and groundwater level variation and discharge in our watershed. And now what we are studying is the interaction between stream aquifer interaction. how is the system, what the groundwater flows to the stream using a distributed temperature system sensing, DTS with fiber optics, to identify the stretches where we have groundwater, well, let's say effluent groundwater, or some stretches with influent stream water. And we are now looking at the different geochemical conditions, how is the impact of the groundwater quality on the surface water and on the other hand. And also in these different hyporect zones, how it impacts the biology, the microorganisms that are developing there, what is controlling. Is the nutrient supply, surface water or from the groundwater, or is the temperature, the stable temperature of the groundwater that maintains the bottom on a quite continuous temperature. And there's a student of us that is studying these microorganisms and even the quite smaller one that we cannot see with some experimental techniques there to understand that. That's one point we are studying. And the other one point is the effect of wetlands. If the wetlands, how they work, are they losing water or are they gaining water? How does it work in this system? Because we have a large evapotranspiration. And the reason for that is that some time ago, also Davi Mello helped this, we built a numerical model of our watershed since we have plenty of data. And we had some wells that didn't adjust for any unknown reason. We couldn't adjust that. And after some research, we found out that the riparian zone, which is quite humid, is a drain of water. And we tried to adjust this, changing the hydraulic conductivity and doing some tricks, but nothing worked. And we said, well, we have to study the water balance in this area to understand how much water we are losing there in terms of evaporation and evapotranspiration. That's what we are also studying in this watershed.
Well, that's fantastic, and I really enjoy going out into the field with you and your students, and it was extremely interesting. And it shows the value of having decadal monitoring data, you know, that you can really get good numbers in. And it's amazing the differences. Although, you know, after the fact, you would anticipate such large differences in water partitioning with these different types of vegetation, from fallow or from no crops to grasslands with shallow roots, and they allow a lot of water to recharge. And then the eucalyptus, which grows so quickly, and, you know, over a life cycle of about 5 or 6 years, and then they harvest them. Those plantations were just amazing, and they put most of the water back into the atmosphere. So extremely interesting. And, you know, we talk a lot about climate and the importance of climate, but land use has a big impact on water resources, and we need to understand these effects, you know, to understand the system. So I really appreciate you taking the time to talk with us today, and I really enjoyed the Congress. And there was one presentation where one of the presenters mentioned that maybe Brazil could feed another billion people globally in the future. And I think you are already feeding a lot of people. I mean, the exports of soybeans and everything to China, $100 billion a year. I was looking at it. So it's really amazing. And I think it's a combination of the climate and the land and the soils. And then, you know, all of the research that you do with Embrapa and ANA and all these other groups, you know, to improve crop productivity. It's extremely impressive. So thanks a lot. Our guest today was Edson Wendland from University of San Carlos, and really appreciate your educating us on Brazil.
Well, really, thank you, Bridget. Before finishing, I would like just to say this food production is possible because they are researchers from Embrapa and from the other universities, the agricultural companies and schools. They are developing seeds, genetic modified, and in the same area, we can harvest 3 times a year because there is plenty of energy, there is land, and there is time. And what we need is water. If we have enough water, we can harvest 3 or 4 times a year, in the same area, and that increases enormously the productivity and the food production of the world. That's the reason why they say perhaps we are already feeding 1 billion people, and if everything goes further, we can reach up to 2 billion people fed by Brazilian production. And I think the central question is the availability of water and the sustainable use of water, so not to disturb the system that much. So, and just to say, of course, all the work that has been done here, we were talking about, has been done by our students, undergraduate, master, doctor students, and postdocs. A lot of people that already joined our research group, our laboratory, and they spend the time there and do a lot of nice works. I'm always amazed about the engagement of our students and the capability that they have to do research and develop new questions and write papers and all that. And it would be a pleasure to have more students from abroad joining our group and sharing all this knowledge and getting out of the experience to go to the field with us, do some monitoring, really work at the field and work at the laboratory and try to give them a complete view. And especially to you, I thank you very much for visiting us last month. And it was not the first time, it's already the second time you have already been here. And always when you come is really a great pleasure for us to have you visiting and giving the students the opportunity to discuss what they are doing and explain it as an exercise, another important exercise for the students. So I enjoyed really much your visit and all the trip we have done here in the fields, different fields, and you are very well welcome again here in São Carlos. I hope we find the opportunity again to have you here visiting another projects that we are thinking about. And I hope that the people that are listening to us also enjoyed the conversation. For me, it was really a nice talk. The time ran surprisingly more than 1 hour already. So Bridget, thank you very much. I think I talked too much, and next time I will control myself better. Thanks so much.
No, thank you so much, Edson. And I look forward to visiting again. And I hope you will send some students up here so we have more exchange, and
Yes.
really enjoyed it. Thanks. And I hope that the drought situation will improve, that you will get out of this drought with this upcoming rainy season, hopefully. Thanks. Take care.